Yeah. So suppose you have a linear map. Let's give this a name. So maybe phi is good. So let's call it f. Phi is too often used. So f from v to w, linear map of vector spaces. Then it induces map at all various levels. So not just tensor algebra or something, but at every level. So you have a map from T and V to T and W. Then F induces maps, and they are sort of unique maps. So maybe you can call it TNF if you like. Next, maybe okay, sure. So we use both notation, this lambda notation as well and Ext notation as well. Ext and V. So maybe I'll use lambda notation for map, and of course it also induces map at the level of symmetric, sim and V to W, sim and W. So sim and F, and then the corresponding algebras as well. So maybe I'll skip writing the algebra. And the maps are, so all this is because, it's not that complicated to give these maps, because, you want to give a map from T and V to T and W. So what you have to do, you have to give a n linear or multilinear map from n copies of V to T and W, and that will give you induce a unique map from T and V to T and. And there is an obvious candidate. So if you have n copies of V, and and you want to give a map to so maybe I take move this a bit. So if you have n copies of excuse me, if you have n copies of V and you want to give a n linear map to so multilinear map to T and W, the obvious thing is to send it to n copies of W and then compose it with the natural linear multilinear map to T and W. Because T and W comes with this multilinear map. W1 to Wn going to and little W1 tensor W2 tensor Wn. That is this map. Okay, and this map is just you apply F to each component. So A1 to AN going to F A1 to FA. And when you compose this with W, so of course this F is linear in each coordinate, and meaning if you fix, so F is sort of linear. So if you fix the remaining guys, then and then compose it with phi, you still get multilinear. So it's easy to check that this composition and this let's call it F twiddle composed with this is multilinear. So and that's how it will induce T and F. And of course, you have similarly you can do it with alternating guys. So if you send it to X and W, you consider this. So if you look at the exterior algebra, it comes with alternating map to from n copies of W to extend W. So if you compose f tilde with this guy, yeah. So I don't know, maybe E, let's say. Then you get exterior. You get a alternating multilinear map, and if you compose it with symmetric guy, if you send it to the symmetric algebra, and maybe call it phi WS for symmetric, then this multilinear map is going to be symmetric, and hence you will get these induced map. Yeah. So you get these maps at each of these levels, and then if you combine all this, you'll get the map at the tensor algebra level, as the exterior algebra level, and the symmetric algebra. So in the language of category theory, this Tn or Xn and Sym_n are functors, or tensor functors from vector spaces to vector spaces, let's say. And the exterior algebra, tensor algebra, symmetric algebra are functors from vector spaces to algebras. Yeah. General algebras, or symmetric one will, you can say it's functor to commutative algebra, and yeah. So these are so as Tn's, Xn, Sym_n are functors. So, meaning to check that it's a functor, you have to check something else. So, of course, given a map, a linear map, you have constructed maps between the vector spaces. So you have to check that, you know. So one has to check. That T of Tn of F composed G. So if you have F and G, two linear maps such that you can compose them, then Tn of F composed G is same as Tn of F composed Tn of G. Okay. So and similarly for the other ones, yeah. So once you have checked this, and those things are also clear, yeah. So you just verify this. So this is not too difficult. Then in the language of functors, then you can say that Tn's are indeed. And you also have to check, yeah. So once you are in category theory and you want to make some statement, there are a bunch of checks. You also have to check that identity. If F is the identity map. Of course, this is identity, so all this, so Tn of identity is identity, gamma n of identity, and so on. So everything is identity. Yeah, so that part is also, so there is hardly any check there, yeah, because of the way definitions are. So identity map also go to identity. That's another thing one has to check for functors. Okay. And some of these have some nicer properties as well, but let's not worry about it. But what I wanted to say is that it induces map. So not only it sends a vector space to another vector space and so on, it also sends maps to maps between the corresponding gadgets. Yeah. So this is the phenomena which we saw even in when we were doing algebra 3, like home functor and tensor we didn't do, but home at least I think we did. Yeah, so home we saw so functor in the sense we saw this home m dash and home. Sorry for. These are functors, yeah. So one is covariant and the other is contravariant. So the direction of the arrow changes, but they are both functors. Or localization. Did we cover localization? So localization is a functor. So I think we must have done localization, I think, in algebra 3. So localization is also a functor. Yes? So so maybe there are too many things.
How is it a functor?
Say that again.
How is it a functor? Like it should be going from one type of structure to another type of structure, right?
Yeah, so they are functors from R modules to R modules.
Okay.
Okay. Or localization, you can also say so. So these homes are functors. That's clear. Yeah. So if you have an R module A and an R module B, then of course you have maps. Which one is covariant? So you have a map from A to B, then maybe you have a map from let me tell you how this home MB. Yeah, so we know that home home MA is an R module. Yeah. Similarly, home MB is an R module. And if you have a map from A to B, an R linear map, then of course you can. And if you have a map from M to A, then you compose it with this and you get a map from M to B. So you get a map like this, yeah? So phi going to, so let's call this F, then phi going to, maybe a longish arrow, phi followed by F, yeah? You will give you a map from home MA to home MB, yeah? So, so this is a functor. This is also a functor, but given a map from A to B, you don't get a map from home A and to home BN, but you get a map in the other direction. Yeah. So that's why it's called a contravagent functor. So again, it behaves. This behaves well. So if you call this. So F compose G will go to the corresponding map here. Yeah. Here also it behaves in a contravariant way, but it behaves okay. Similarly, localization. If you are inverting, so you have to start with some ring and a multiplicative set. Then of course S inverse M is not just so it's an R module. So of course, if you have a map between M and N, then you'll get a map between S inverse M and S inverse M. Yeah. So a linear map from M to N induces this. So both are in fact S inverse R modules as well. So you can also say that this is a functor from R module to S inverse R modules. Okay. Is that okay?
Yes, sir.
So these are all. So functors are basically these kind of things. So it's from one category meaning it has objects and morphisms and so on. So I don't know if I want. I don't want to do much category theory right now, but so I don't know. Maybe you'll see it somewhere. Yeah. Okay. Okay, so let's get to representation theory. So let G be a finite group, V be a finite dimensional vector space. Then a representation of G is a group homomorphism. So there are various ways of defining it, but the shortest way is to say that it's a group homomorphism from G to GL of P. Yeah. In this case, so our representation is actually such a map, but by abuse of notation, people say that in this case, V is said to be a representation of G. Representation of G. Okay, so we will decode this. Yeah, so so what happens is there's an action of G on V. Yeah, so so we'll write it a little more explicitly what is happening here. Okay, so so if V is a representation of G, then of course you get that there is an action. Yeah, so and then for G in G and little v in V, there is an action of G on V. So G dot V, you define it to be rho G. Rho G is a linear map. Yeah, is an invertible linear map of V. Yeah, so you can apply it to V, and you get something in V. So so this action is so this is a so this is a group action. So that is clear. Yeah, so because so we have to check a few things. So what do we have to check? So EG dot V is rho of EG evaluated at V, where, and since rho is a group homomorphism, it goes to the identity element of GLV, which is the identity map of V. So since rho is a group homomorphism. So identity will go to identity of GLV, which is the identity map. Yeah, and of course, if you have so you have to check G. Yeah, so I hope the direction. Yeah, so the direction should be okay. GH G dot H
So
dot.
for both left and right identities.
Say that there is only one identity in GLV. Yeah, all the groups have only one identity. Yeah, which is whatever it is. Yeah. So so if you apply this, then this is H dot V is rho H evaluated at V, and so you get a vector, and then if you apply G to it, then it's rho G applied to this vector, and this is same as rho G composed rho H applied to the vector V, but we know that rho is a group homomorphism, and group operation in G is whatever G times H, and group operation in GLV is composition. Yeah, so this is same as rho of GH evaluated at V, which is GH dot V. Yeah. So these are the two things one has to check to make sure that this is a group action. So our representation gives you a group action, but it's not just arbitrary group action. Yeah. So arbitrary group action doesn't say, so if you are given a group acting on a set V, then G dot, so G dot, so this each element of G will induce a bijective map of V. Yeah. So it's not just, so of course, every element of GLV induces a bijection on V. It's an invertible matrix or invertible linear map. But it's not just a bijection, it's also linear. Yeah. So there is also so another property we have, moreover, G dot V1 plus AV2 is equal to G dot V1 plus A times G dot V2 for V1, V2 in V and A in the base field. So V is over K. Okay. So here, I mean, the definitions, etc., one can do it over arbitrary field, but we'll assume K to be complex numbers or at least characteristic 0. Yeah. So later on, even complex numbers, algebraically closed characteristic. For all V1, V2 in this, and G also. So for all G in G. Okay, so so if you are given a representation, then it induces an action which satisfies this additional property. Conversely, if you are given a G action on a vector space together with this additional property, it that means the action of G on V is actually linear. Yeah. So so what you get is actually a representation. So you get a group homomorphism from G to GLV. So maybe I'll so conversely let conversely given an action of a group G to G on a of a, let's say, I mean, so definition you don't need finiteness, but it's okay. Yeah, you can think of it as a finite group. Given an action of a group G on vector space V, and such that G dot V1 plus AV2 is G V1 plus A G dot V2 for all G in G, and V1 V2 in V. And A in the base field K. It induces, it gives one obtains a map from G to GLV. Yeah, so what is the map? Basically G going to G, G dot, so G going into the map which sends V to. So maybe I'll call it phi rho sub G. Yeah, going to rho G, which sends V to G dot V. Yeah, so the point is, if G is just an action, then this map rho G is so if since G is an action, so maybe I should write for clarity. Since G is an action, since G acts on G acts on V rho G is basically, so in group theory you must have seen that if you have a group action, this map G sending V to G dot V is actually in the set of bijections of V. Yeah, so this is also denoted by symmetries SV. Yeah, SN SV, not sim. Yeah, SV. So a set of bijections like SN. Yeah, so in that spirit, set of bijections of V. And the additional condition, this condition, the condition star ensures that rho G is linear. Yeah, so that's the definition of linear map. A map from V to itself is linear if this happens. Yeah. So and hence rho G actually is in GLV. GLV, of course, is set of all linear bijections of V, so it is in SV. SV is too big. Yeah, it's set of all permutations of V, so its order is so it is a very big group. GLV is more manageable. So you can think of a representation in two ways. Yeah. So one is you just think of it as a group homomorphism from G to GLV, which is the which we are calling the definition. Or you can think of it as a group action where the action is linear. Yeah, the action map is linear on induces a linear map on. Okay. So either way is fine. Any questions? Okay. So so let's see some examples. Yeah. So maybe what's the first example? So so maybe we should take a group. Yeah. So maybe we'll keep the group arbitrary, but maybe we'll keep the vector space somewhat simple. Yeah, so one dimensional. So let V be a one dimensional vector space. So let V be C. Yeah. So it's the base field, and G a group. Finite group. So this is a Poisson representation of finite groups. Yeah. So what is a representation? So by definition, a representation of G on V is GL of V, and what is GL of C? GL of V in this case? What are the invertible linear maps of C?
C star.
C star, yeah. So you take, so it's 1 by 1 matrix which is invertible, which means you take every invertible element of C, yeah. So it's C star, and rho is a group homomorphism, yeah. So you can say a little more. So since G is a finite group, what can you say about the image of this group homomorphism?
So it would be a root of unity.
It will be into?
It would be a root of unity. Sir.
Yeah, so images is a finite set, but it's also, it has to land in the unit circle. And in fact, it has to be one of the roots of unity. So note that phi G for order of G is same as phi of G per order of G, and G per order of G is identity. So is this phi rho of E, which is 1. Yeah. So that tells us that phi G is a root of unity. In fact, you can say it has to be nth root of unity, where one of the nth root of unity, where n is the order of G. Yeah. In particular, you can say so. In particular, you can also say that rho G, absolute value of rho G is 1. So it maps onto the unit circle. Yeah. So though this I say some linear map, but for finite groups, of course, it's going to be in the image is going to be C star. Okay. So what's an example of one such map? So one such map is you just send everything to the element 1. Yeah. So maybe 1A rho is the trivial homomorphism. So then, of course, that means the image of everything is identity. So the action on B is identity. Yeah. So it gives you a trivial action. Then G acts trivially on B. So this is called the trivial representation. Called the trivial representation. Okay. So for one-dimensional representation, it's pretty straightforward. It's given by maps to C star, and the one of them is trivial, and so on. So for when G is abelian group, we'll see that these one-dimensional representation more or less determines all representations of G. But when G is non-abelian, then of course you can get something more complicated. Okay. Now maybe I should give you some more examples. So, yeah.
Sir, what are you exactly referring to when you say representation? Is it phi or?
So it's the map rho.
Sorry, rho.
Yeah, rho is The trivial representation. So representation means a group homomorphism from G to GLB. Yeah, or which also determines an action of G on B. Yeah, so you can think of it as an action of G on B. So if you are given a group homomorphism from G to GLB, it also determines an action. Yeah, which is linear. So you can think of it as both ways: a linear action of G on B, or a group homomorphism. So to give a linear action also means you have to give a map from G to GLB, or for each G you have to give a action. So I mean, you can, and action is what is an action? It's a map from G cross V to V. Yeah, that is what an action is. G dot V gives you, so it's a map from G cross V to V, which induces a map from G to sim V, SV, but the image lands in GLB if it's a linear representation. Yeah, it's a representation. Is that okay?
Yes.
Yeah. So so maybe another example would be so maybe from group action. So say G. So let's say G acts on some set. Acts on set X. Okay. So you can look at the vector space. So maybe finite set. Yeah. Finite set X. So so that I mean the vector space we get is finite dimensional. Though, so I mean, when you take definition, it's not necessary that be finite dimensional. Yeah, but I have so we will restrict to finite dimensional representation. Okay, so those are yeah. So you can always sort of reduce to finite dimensional setup in some way. Okay. So G acts on a finite set X, then yeah. So what it does, it's so of course if X doesn't have a vector space structure, you can't do anything, but you can of course construct a vector space out of X. Yeah. So which is you look at a vector space over X in the sense that it has a basis consisting of elements of X. Yeah? So let Vx be C vector space consisting with the basis consisting of elements of S. So I mean, so Vx is basically Cx1, Cx2, Cxn. Yeah, where X is X1 to Xn. Okay, so if it has n elements, you can make this. Yeah. So now you can, of course, think of. So now you can give a linear action of G on B. Yeah. So G dot V. So it's enough to say where xi's go, and then you extend it linearly. Yeah. So maybe I'll just say what it is. Yeah. So if so, first of all, I'll say where the basis goes, and then we will do. So G of xi, and G dot xi should be G dot xi in that sense. So it's sort of maybe Yeah, it seems a bit funny, but g dot xi meaning 1, 1 xi should be g dot xi. Yeah. Where in the second is g action. This is g action on x. We are trying to define the action of g on vx now. Yeah. So more generally, g dot summation ai xi I equals 1 to n. So this is how a typical element of vx looks like. Is summation ai, summation ai g dot xi. So g dot xi is going to be some xj. Yeah. So it will be yeah. So I should have actually yeah. So which is equal to xj for some j. So G induces a permutation of x1 to xn. Yeah. So this is some x. Yeah. So it induces. So this this by definition is an action of G on Vx, which is linear. Yeah. So Vx is a representation of G. And since it comes from this permutation, is sometimes called a permutation representation. It is called a permutation representation. I mean, it's clear why. So if you look at the map as well, so if you think, so it will induce a map from G to GLBX. Yeah. Set of linear maps from Vx to Vx. And if you consider these, so GLBs are linear maps, but if you fix a basis, it's equal to GLN of C. Yeah. So this is equal to this. So once you fix a basis, this isomorphism is fixed with respect to the basis x1 to xn. So if you think of this identification of GLBX with respect to matrices using after fixing the basis x1 to xn, then what will rho G be? What will be the matrix? So rho G will be a permutation matrix. Yeah. So so G dot X is what does G dot Xi give you? It gives you some Xj. Yeah. So rho G is a permutation matrix. You know what a permutation matrix is, yeah?
Yeah.
So yes, basically it has each column and each row has exactly one, yeah, and rest are zeros, and it induces a permutation on the basis. So that's the reason it's called permutation matrix. Okay, so that's another. So so this action gives a map from G to let's say Sx, and Sx sits inside GLVX nicely under this permutation thing. Yeah, and this is how. So this composition is basically your representation. Okay. So there's no mystery to it. Any questions? There is also another representation which is a very crucial representation, which you may have, which you have the construction you have sort of seen. So I think maybe, so if let G be a group, be a finite group, then you know this this group ring, yeah, KG. You know this this guy? Do you remember what KG is? Is there anyone who doesn't know what KG is? So everyone knows what KG is, yeah? So, but anyway, maybe I'll just say it's not that difficult to define. So it is as a set, it is KG, or rather sums of the form AGG, where AGs are element of K. G. Yeah. So this is how this group ring looks like. So it's actually actually a ring. So not only you can add elements, but you can multiply it as well. But we will think of it as a vector space. So it's also a vector space. Yeah. So on this also you have a, since it's you have a representation which is sort of natural. Yeah. Yeah, but yeah, so I don't know whether it's left or right. Yeah, so let's see. So so you have a representation, you have an action of G on KG to KG. So there is a notion of left. So what we have defined is a left representation. Yeah, in the sense. So even if you have a right representation, so they, I mean, so if you define it in this way, in terms of maps, this left or right is sort of gone. It's a ring it's a group homomorphism. Yeah, but if you define it in terms of action, then it induces a left action, but it can, I mean. The way, so sometimes even if it's a right action, it will give you a group homomorphism. Yeah, right. So left and right is so every left action you can translate it into a right action and so on. But sometimes it's easier to, so the natural thing to write is sometimes left action, sometimes right action. So I'll just see. Yeah, I'll try to keep everything as a left action. So or one can just write it as a group homomorphism. So G comma summation AG G in G. So sorry, so this is not a good way to write. Too many G's, yeah. So let's call this H. So so of course you can send it to yeah. So I'll just send it to summation AG H G. And hopefully this is a, so if I have H1, H2. Yeah, so I think this is okay. Yeah. So this will, so basically, yeah, so this is okay. Yeah, so what happens is, so here the coefficient of G is AG. What is the coefficient? So G in G. What is the coefficient of G here in this thing?
H inverse.
Coefficient of G is H inverse G. A sub H inverse G. Yeah. So A sub H inverse G times H. So you get the coefficient is H inverse G. Yeah. So just keep that in mind. Yeah. So this is, and of course, this is, and this should also be linear. Yeah. So one has to check that this is a linear action. So, but I mean, the way it is defined, it is clear that it's linear. So the coefficients all pull out. Yeah. So so note that the action is linear. Action is linear, meaning if you take two of them, add them, you get you can split it again. Yeah, and be as well with scalar multiplication. So it is a representation. So Kg is a representation. So this natural map. So Kg is a representation of G. Okay. And this is called the regular representation. So it's a very important the regular representation of G. So this is a very important representation. In some sense, every sort of reasonable, every what is called an irreducible representation of G is sort of sub-representation of a regular representation. So we'll study this regular representation in more details. Yeah. So it captures. So note that. So what is the dimension of Kg? It is
Mod J.
Say that again.
The order of the group.
Is same as the order of the group. Yeah. So it's a high dimensional representation, and you know the kernel of this group homomorphism from G to Kg is also trivial. Yeah. So G actually embeds into, because of course I mean, G acts on G via permutations. Yeah, so it's a faithful action. It's a faithful action, and that leads to this this thing. Yeah, so you can think of this as G acts on itself via left multiplication. Yeah, so that, and then we have built it out, and then you can. So it is an example of a permutation representation as well. Yeah. But it's a special kind of representation. It's called regular representation. So we will see how one can break this. So as I said, every representation sits inside this. So in particular, this has a trivial representation inbuilt in it as well. Yeah. So we still have 2 to 3 minutes. So maybe yeah, so I haven't really talked about subrepresentation. So maybe I'll define subrepresentation and then tell you why the trivial representation sits there. Yeah. So definition, let V be a representation of a group G. So if I don't say you always assume finite group. Yeah. So this means you have a map from, so you can think of it as a map from G to GLB, or you can think of G action a subspace W of V is called subrepresentation. Representation of V if W is stable under G action. Yeah. So if rho G of W is in W for all W. If for all G, so and this should be true for all J in G. Rho G of W is in W. Yeah, so I W is stable under G action. Okay, so basically then so rho induces a map from, so rho to start with was a map from G to GLV, but if you know this property, so star implies that you get rho, maybe rho W, let's say, from G to GLW. Yeah, because I mean, the image is again going to be a linear, it's going to be a linear map of W, and it actually lands in and is invertible. Yeah, so it induces a map from G to GLW. Yeah, so that's what a subrepresentation is. So of course, this what is a trivial subrepresentation of KG? So on what subspace of KG G acts trivially?
K.
But K is not an element of KG. KG is this guy. Yeah. You mean E times
Yeah.
K times E? Yeah, so that is not true because, E will be sent to G when you multiply, yeah? Permutation multiply. So, or rather H times 1 times E will go to H. Yeah, so it's not, the action is non-trivial. Yeah.
The subspace generated by summation GIs.
Yeah, exactly. Summation GIs, yeah. So remark maybe. So consider the subspace, let's see, I don't know, W to be A times E plus summation, I'll just write it, A times. So is the subspace generated by sum of all the elements, yeah. Summation G in G, A times this, A in C, A in the base K field. So this is of course a subspace, yeah. You're just taking the subspace generated by sum of all the elements of G, yeah. And of course, the action sends this guy to itself because it just permutes all of so H times W is W for all W in W. Yeah. Because it's so if W is A times summation G, then H times W is A times summation HG. but summation hg as g in g varies in g is same as summation g. Yeah. So it is so W is a trivial representation of G, and it is a sub representation of KG. So you have seen an example of a sub representation, and you also saw that it is trivial. Now, okay. So next time we will talk about. So if you are given a sub representation, you can always form a complementary representation. So this result uses the fact that the field is of characteristic 0. It's not true in general, and then we will go on to discuss irreducible representations and all. Okay. Any questions?
Sir,
Yes.
in this trivial sub-representation,
Yeah.
we can also, this can hold for any symmetric polynomial in all elements of G also, right?
What do you mean by symmetric polynomial? So there is KG, the description of KG is just this, yeah?
No, I was thinking like summation GI, GJ, but that is same as summation GI.
Summation GI, GJ, yeah. So yeah, so if you so it's some and the vector space generated by that, yeah. So it's going to be just this, yeah. Summation GI, GJ. If you sum it with you know, maybe so you sum over all i's, sum over all GIs in G, you get you know, same as summation G, yeah. And so you'll be counting it a certain number of times, but that's about it.
But like product of all GIs?
Product of all GIs is whatever it is. So it's going to be, so subspace, and so it's going, so a product of GIs is going to be some element, yeah, of G.
Yes, sir. So the subspace generated by that?
That won't be a trivial representation. So so if you take any particular element of G and consider the subspace generated by this, it's not going to be a trivial representation, because you know, the group action is transitive on this thing. Okay. So it comes from the group action of G on itself, and that action is transitive. Yeah. So it won't lead to a trivial representation. Okay.
So is this a unique trivial subrepresentation?
Yeah, so there is only one trivial subrepresentation of KG, which is this one. There is no other. Okay. So that also we will see once we try to understand KG better, then we will see that there is only one trivial representation. Okay. Any other questions or comments? Okay, so maybe I can stop recording.